Hi everyone, Mr. Canistero here. In today's video, we're going to do an example motion graph problem. And so our objective is we're going to solve for the displacement and acceleration of an object using a velocity versus time graph. So one of the things I like to do with a lot of these problems is kind of apply a strategy you can use that works for many types of problems. For motion graphs, I really like to think about them this way in terms of steps. Step one, I always like to think about the types of motion that are occurring. So when I see a graph, I like to think, is this a constant velocity? Is this an acceleration happening? Is it standing still? After I've done that, step two, I like to break up and label the problem. So if there is a graph where it's doing a bunch of things, so changing, going up, down, left, right, etc., I like to break it up into a bunch of little pieces and then just examine one piece at a time. Then step three and four, the big facts of a velocity versus time graph are that the slope of the graph corresponds to the acceleration and the area underneath, or the area between the graph and the time axis, corresponds to the displacement of an object. So let's go ahead and apply this strategy to an example problem. First one, let's solve for the displacement acceleration after 4 seconds for some object that has this type of motion for a velocity versus time graph. So what I see here is where the graph is staying straight, because this is a velocity graph, if it's staying at 6 meters per second, that's meaning it's staying at 6 constantly from 0 to 2 seconds. So this corresponds to constant velocity, this piece. Then from 6 seconds down to 0, it looks like over the course of that 2 seconds it's slowing down. So this corresponds, of course, to a negative acceleration or a deceleration. And at 4 seconds, it looks like it has a velocity of 0, so that means it finally comes to a rest at 0 seconds. So that's good stuff to know. We know then when we're trying to find accelerations and distances, it's going to be moving for a little bit and then it's going to be slowing down. So that's something to think about. So step two, break it up into two pieces. So what I'm going to do is from 0 to 2 seconds, I'm going to call piece 1. And from 2 to 4 seconds, I'm going to call piece 2. And I'm just going to examine each piece at a time. So next, our problem is solving for the displacement and acceleration after 4 seconds. Let's go ahead and solve for the accelerations first. So I'm going to go ahead and erase this, we have some room. So let's solve for the acceleration. So from 0 to 2 seconds, we see the following. Recall the acceleration is the slope of the line. So if the line is horizontal, we know that the slope, the rise of a run, because it has 0 rise, the slope has to be 0. Another way to think about it is, because this is a constant velocity and acceleration represents your change in speed, if you're moving at a constant speed, your speed's not changing. And so we know the acceleration from 0 to 2 seconds, it's got to be 0 meters per second squared for either of those two reasons. Now, we also know from 2 to 4 seconds, yeah, this graph, it's definitely slowing down. There's a deceleration. We know we're going to get some kind of a value. So we go ahead and we find the slope. Remember that the slope is equal to the rise over run, or, your delta y over delta x, y2 minus y1 over x2 minus x1, whatever you float your boat. Our rise, it goes from 0, it starts at 6 and it goes down to 0 meters per second. So the change in velocity is it started at 6, went to 0, it went down by a minus of 6. The run, the time it took to do that was over 2 seconds. So our slope is negative 6 over 2, which is negative 3. So our acceleration is negative 3 meters per second squared. And so there we found the acceleration for both segments of this graph. Now let's go ahead and find the total displacement of the object from 0 to 4 seconds. So to find the total displacement, that corresponds to the area under the graph. And so once again, I'm going to use my segments 1 and 2. And I'm going to shade the area. So we shade the whole thing. This is the area we're trying to find. If we find the area of this trapezoid, we can find the displacement. Now, trapezoids are fun things to find the area of. Instead, what I'm going to do, I'm going to break it up into two pieces. Again, piece 1 and piece 2, because I see that piece 1 is simply finding the area of a rectangle. Piece 2 amounts to finding the area of a triangle. So the area of piece 1, it's a rectangle, so the formula is base times height. My base is 2 seconds. My height is 6 meters per second. So the first area is 12 meters. And then for the second one, formula for the area of a triangle is 1/2 base times height. So I do half. The base is again 2 seconds. My height is 6 seconds, so 2 times 6 is 12 divided by 2. I get 6 meters. And so my total displacement after 4 seconds is just the 12 plus the 6, which ends up being 18 meters. And there is the acceleration and displacement for a fairly simple graph. Now, a lot of times in physics, we have graphs that aren't as simple, where, for example, the velocity ends up being in the negative range, as shown here. So first off, when I see this object, if I try to break it apart, I see that in the beginning, it starts out with a positive speed. Then somewhere in the middle, right at 2 seconds, it has a speed of 0, and that means it comes to a stop. And then towards the end, it's speeding up, but it has a negative velocity. So this is indicative, this graph is indicative of a ball being thrown up in the air and then coming back down. Because we know at the very top of a ball's flight, if you watch the other videos or just know from physics, the speed is 0. So one of the things I might want to say is, when the line crosses through the 0, this is stop and turn around. So what we're going to do now is we're just going to keep applying our physics strategy. We're now going to find the slope in the area once again. And again, slope will give us the acceleration. The area will give us the displacement. So I'm going to erase a little bit of this just so we have some room to write. So first thing, we'll find the acceleration. Again, the acceleration is the slope, which is the rise over run. And for this, you can pick any 2 segments on the line, doesn't matter. I'm just going to go ahead and pick where it starts and halfway through. Because it's the same line the entire way through, that's acceptable. So my rise, it starts at 10, ends at 0. My rise is at negative 10 meters per second. My run is 2 seconds. And so I have an acceleration, in this case, of negative 10 over 2 of negative 5 meters per second squared. Now, to find the total distance, same idea. I'm going to go ahead and shade my area. The one key piece of this, though, is, unlike in math where they say there's no negative areas, when you're talking about velocities, if you have a negative velocity, that means you're walking backwards. So if we want to find your displacement, if you walk forwards and backwards, that backwards distance you walk is going to kind of subtract away from that forwards distance. So we really need to treat this triangle down here as a negative displacement. So we'll do the upper triangle first. I'll call the upper triangle triangle 1, and the bottom triangle I'll call it 2. So for the area of triangle 1, it's again half the base, which is 2 seconds, the height, which is 10 meters per second. And so 2 times 10 is 20 divided by half. We get an area and a distance of 10 meters. The area for the second piece, it's a half. 2 is my base, and this time my height is now negative 10, so I can just keep the negative. That makes it easier to think about. And I get a distance of negative 10 meters. So therefore, my total displacement, when I add it, I get a displacement of 0 meters, meaning the object started in the exact same place. Ended in the exact same place it started, which, because we already analyzed the graph and said, hey, this is a ball being thrown up and down in the air, that kind of makes sense, because this is a ball being thrown up into the air, going back down, and ending in your hand in the exact same place it started. So it makes sense that you get a displacement of 0 because it starts and ends in your hand. So that's it for today's video. Hope that helped with you guys thinking about motion graphs and the concepts of slope and area.